Hello, welcome to WeatherWise. I am your host, meteorologist Nathan Scott. In this episode, we're going to get back to basics. We're going to talk about cloud types. I'm sure you know the difference between a cirrus cloud and a cumulonimbus cloud, but we're going to get a little more in detail. Do you know the difference between a cirrocumulus cloud versus a altocumulus cloud, or cirrostratus cloud versus the altostratus cloud? We'll break down on what those differences are. Also, have you been to the ocean and you notice there's a wind that comes into play and it feels good out there when it's the afternoon hours? Well, that is known as a mesoscale phenomenon known as the sea breeze. We'll talk about why sea breeze develops in the first place and how that sea breeze actually comes into play when you're trying to do forecasting in a place like South Florida. Finally, we'll wrap up things talking about another mesoscale phenomenon known as a valley breeze. And that's very common here in Arkansas and especially the Ozarks. But let's start off here with the cloud types. When we take a look at this chart, that is from the National Oceanic Atmospheric Administration. It shows the basic cloud types according to the levels that they develop. You probably remember back in middle school, the clouds are named using Latin roots, the prefixes. So you look at what's above the chart. Cirro is a curl of hair, meaning high above the surface. Alto is a mid-level cloud. So anything that has alto attached with it means it happens in the middle parts of the troposphere. Strato means layer. Nimbo means it's producing precipitation. So nimbostratus means it's a low cloud, but it's producing precipitation. Now that precipitation could be rain, sleet, snow, and that's just determined by the temperature profile, of course. And then we have cumulo, which means heap. So you look at these different types of clouds, and we're going to break it down by low, mid-level, high level, and then what's known as convective clouds. We'll start off here with the lowest type of cloud, the nimbostratus. And that can develop at the surface, and if it is developing at the surface, it is a cloud, but it's known as, of course, fog. And nimbostratus can go up about 5,000, 6,000 feet above the surface. Once you get above 20,000 feet, then you get into the high cloud range. That's the cirrus and the cirrocumulus. That cloud is actually made of ice crystals, because it's so cold that temperatures are well above freezing in that part of the atmosphere. That's why it has a different look. And we'll get more into why cirrus looks differently in terms of the type of ice crystals that develop within that cloud. Mid-level clouds, once again, alto. So we have altocumulus or even altostratus. Then you have the convective type of clouds. Cumulus, those puffy cotton ball looking clouds. Sometimes they're flat base and they don't have much of a top or a cloud height to them. But when the atmosphere is colder than the surrounding bubble of air or thermal of air, that cloud will continue to grow and grow and grow. So it goes from a cumulus into a cumulus congestus and then eventually a cumulonimbus. And of course, a cumulonimbus is when you have the anvil head develop at the top of the cloud. And the reason behind that is because as the cloud continues to grow, it hits a critical threshold between the troposphere and the other part of the atmosphere known as the stratosphere. And the temperature from the troposphere to the stratosphere actually starts to go in the opposite direction. So instead of cooling with height, once you reach the pivotal point between the troposphere and the stratosphere, your temperature actually climbs with height. And that's why you get that anvil head shape, because it hits that and it's almost like a wall and the cloud spreads out in all directions. When we talk about the different types of clouds, of course, clouds can develop in many ways. You can have a typical sunny day, and then just because the land goes through uneven heating, you have these bubbles of warm air that develop, and those bubbles of warm air cool, condense as long as the atmosphere, once again, the surrounding environment is colder than the actual bubble of air. That bubble of air will eventually cool, condense, form a cloud. It's the same reasoning behind a hot air balloon. Hot air balloon is hotter than its surrounding environment, otherwise it won't rise. But a cold front produces more thunderstorms because of what's happening with that air. It is making its way across the land here with this diagram, and it has a sharp angle to it. So as that colder air is heavier than the warm air in front of it, it forces that warm air up, and you get clouds that do form. With a cumulonimbus cloud, that anvil head, because you have the wind coming in, say from the west in this direction, it will shear or kind of fragment the clouds at the top of the cumulonimbus and spreads it to the east. So you have what's known as one type of cirrus, well advanced of a cold front, and then that cirrus may get a little thicker before you run into more of the alto cumulus at the lower levels. And you can see this. You know, you have cirrus maybe 1 or 2 days in advance before an actual cold front arrives or a boundary moves in. So your clouds are always telling you certain signs that the weather is changing. And of course, you know, frontier days, people paid attention to the clouds and what was going on. That's why we have the whole saying, red sky at night, sailors delight. Red sky in the morning, sailors take warning. So it's just because of the clouds and how those clouds signify there could be a front or storm headed in the viewer's direction. So the cold front is more likely to produce thunderstorms, but a warm front does also produce thunderstorms. However, the angle of a warm front is not as sharp when you compare it to a cold front with this 3D diagram. So it's from the surface part of the warm front, it goes into a nimbostratus, then altostratus, and a cirrostratus, then a cirrus. And you can clearly see that as well. Your cloud deck gets lower and lower and lower as you get closer and closer to the warm front. And it may happen within a day, it may happen within just a few hours. So when you take a look at the sky next time, try to identify what type of cloud you're looking at. Is it a cirrus? Is it a cirrostratus? This is from, once again, the National Weather Service or National Oceanic Atmospheric Administration. This is a cloud chart. You can find this online. But there you see, cirrus, very thin, very wispy. And there's more specifications on what type of cirrus these are. We're not going to get into that in just 1 second, or just at this moment. I'm going to have a cloud expert hopefully come on the show that has a degree in pretty much clouds, and she has a really cool Facebook page to identify every single cloud that can be found across the world almost. So hopefully we can get her on in the future. But there you see cirrus, thin, filters out the sun. The sun's never fully covered up. But then we have something known as a cirrostratus. So this is a thin deck of cirrus, but it's so thin that the sun is still seen, and also you notice this halo feature. Remember what I said, cirrus clouds are made of ice crystals. Well, when you have cirrus clouds that have hexagonal plates, those hexagonal plates bend and change the light to produce this effect. So next time you have a cloud deck that's filtering out the sun, but you can see a halo, then that is known as cirrostratus. There's something called altostratus, which I'm going to get into in the next little bit here. But cirrostratus can produce very vibrant sunrises and also sunsets. So remember that next time you're out looking and you see some cirrostratus or some cirrocumulus, you may be in store for a really beautiful sunrise or a sunset. Altostratus. Now the difference in this is we can see the disk of the sun, but that's it. We can't see anything else. So that tells us this is a thicker type of cloud. And usually you see this a lot in the winter before, snow is heading your direction or maybe rain. Altostratus is more common in the winter months for the most part. And altostratus can be thick, it can be opaque, but also you've got what's known as lenticular clouds. Now this is really cool. People think they look like spaceships, and they kind of do. They can be just stuck over a mountain. They don't move. And we'll get into maybe some more mountain weather in upcoming episodes, but this is something I've never seen, but you have to be in the right location. So you have to be over a mountain range to see something like that. Very cool phenomenon to see over the mountain range. Rocky Mountains, Appalachian Mountains, it happens in those locations from time to time. Not a guarantee. And then you see the altocumulus here. It's definitely a thicker type of cloud. You see it's got more of the darker colors because the cloud is actually blocking out some of the light, producing the shadow effect. And altocumulus clouds are very layered as well. Sometimes you get gravity waves. So you see, like in the satellite view, where it looks like waves are moving across the sky because they're kind of broken up in rows. Next type of cloud, of course, we're all familiar with is the cumulonimbus. You see it is kind of a beautiful photo, unless you are underneath something like this, but you see the bubbling nature of the cumulus conjuntus in front of it, right here where my cursor is, and then behind it, here's the anvil head. So you see that massive anvil head. That's a probably supercell thunderstorm that's forming in that photo. Then you have cumulus and stratus mixed here. So this is all mixed, and then sometimes you have stratus. This happens a lot in the mountains, very low hanging cloud. Can look a little ominous at times. Can be along with scud, but no worries with this type of situation. Of course, stratus, very thick, blocks out a lot of visibility, especially when it's fog. The stratocumulus, it's a beautiful thing to see, but it can ruin a forecast because it happens. It's very thin, but it's also very thick. It can block out the sun, and it may only be a couple hundred feet thick, but that can bust a forecast easily, and that's happened a lot, especially on the sides of the mountains I've dealt with in Tennessee. And there you see more cumulus and the evolution of cumulus. So it starts out as these little fragmented pieces as the daytime heating happens, and then with more daytime heating, that bubble of warm air continues to rise, cool, condense, and it forms into more of these fair weather cumulus. And if they continue to grow, then you have, of course, the cumulus conjuntus, and then it builds into a cumulonimbus, and showers and thunderstorms bubble up. So that's just a brief overview of cloud types. And we'll get more into cloud types and really try to break more down in upcoming episodes. We're going to go ahead and go to a break. Next thing we'll talk about is a sea breeze. It's a very small scale event, but it can produce big impacts for some parts of the country. Stay tuned. Welcome back. Now the topic is going to be about the sea breeze. If you've ever been to the ocean, you have noticed this, I'm sure. If you're out in the morning, the air could be calm, but then going to late morning through the early afternoon hours, the breeze picks up and it feels good. And if you look at a weather map with surface observations, there's a huge difference in what the temperature is at the coast versus just a few miles inland. The reason behind that is because of the sea breeze. So what develops a sea breeze in the first place? Well, take a look at this. We got the temperature over the land around 7 o'clock for this example in the morning at 71 degrees. The water, though, is 75 degrees. As the sun continues to climb above the horizon, that sun is going to heat both surfaces, the water and also the land. However, because the light penetrates so far down into the ocean because light can go all the way down for several hundreds of feet. Water takes a longer time to warm up versus the land. The land is going to heat up much faster. So now, say around 11 o'clock, the temperature is warmed up to 82 degrees. Meanwhile, the water is unchanged at 75 degrees. What happens with this is the land continues to warm up 87 degrees around 1 o'clock. This air is going to start to rise just because it continues to warm up. Warm air is going to rise around its surrounding environment. It's colder, or cooler, I shouldn't say colder, but cooler. This will develop an area of low pressure because warmer air is lighter than colder air. Meanwhile, over the ocean, the cooler air will start to sink down, and that will develop an area of high pressure. In meteorology, this is how physics works, air flows from high to low. So with this mechanism beginning to develop, you're going to have what's known as an area of cooler air that will start to build and push towards the low pressure developing over the land. So therefore, we're going to have a miniature cold front that develops. And this cold front is going to continue to slide its way to the land or to the coast. And when this happens, this front is going to lift that warm air in advance, and it can produce those pop-up showers and storms. You see this very frequently in Florida. That's why you can pretty much expect most days there's going to be a pop-up shower storm anywhere along the Florida coastline, whether it's the East Coast or also the West Coast at times, just because of this mesoscale or microscale event that happens with the difference of the temperatures, the land versus the water. There you see an area of high pressure develops above the low pressure, and then an area of low pressure develops above the area of high pressure over the ocean. So it is a cycle that will continue throughout the day. And as the sea breeze, for example, comes from the east coast of Florida, you have one that develops off the west coast of Florida, and they continue to push inland. Those shower and thunderstorm bands will move more and more inland, and sometimes those sea breeze fronts actually clash with one another. That produces more lift in the atmosphere, and you could have an enhancement of showers and thunderstorms that develop over central Florida in some cases. So you're in Florida, that's why you have to expect shower and thunderstorm chances, but anywhere along the coastline, especially the East Coast, you have this sea breeze front develop. Not the case for the West Coast, because the West Coast, the water temperature, of course, is much cooler because the ocean current is coming from Alaska and from the Arctic versus from the tropics along the eastern sides of continents. This sea breeze front will actually switch directions at night. So everything will go in the opposite direction. High pressure will develop over land because land will cool faster than the water overnight, and you'll actually have something known as a land breeze. You'll see that if you go out around sunrise, you'll look off to the east if you're in Miami or Fort Lauderdale or anywhere along the East Coast, you may see a band of clouds in the distance over the ocean. And that's because the land breeze developed a front, and that front developed clouds or maybe even some showers and thunderstorms over the ocean during the overnight hours. Another phenomenon that happens here in Arkansas is known as the valley and mountain breeze. I'm going to close out weather-wise with that topic. Stay tuned. The final topic for this episode of Weatherwise involves what we see here a lot in Arkansas and also any mountainous regions across the country. I'm talking about the valley breeze. And how does that work? Well, once again, it's very similar to a sea breeze. The sun is going to heat up the land, but this time the land is going to start to warm much faster according to the elevation. So we have a pocket of warm air that develops in one part of the mountain. because once again, land absorbs the heat unevenly. Some rocks are going to absorb the heat much faster than, say, some areas of wet soil or where it's going to be more shaded. So with this example, we had the low pressure developing right around the middle part of the mountain. Remember, warm air rises, and that warm air is going to continue to rise, and as it rises up along the slope of the mountain, it cools, condenses, and it forms clouds. You see this a lot, especially along the Appalachians, where one side of the mountains will be stuck in clouds because there's other factors at work here. It could just be a breeze that goes up and over the mountains, and we'll talk about more of a downsloping wind in future episodes, which can actually produce over 100-mile-per-hour winds in some cases across the country, even when it's sunny. That's just because the orientation of that wind has to be perpendicular or at a 90-degree angle according to the mountain range. But with this example, we're just talking about this warm air going up along the slope of the mountains, forms a cloud, maybe even a pop-up shower storm. So it could be sunny everywhere else, but there could be one isolated pop-up shower thunderstorm that develops because of this case. Of course, if you're in a mountain range, you've got several valleys. So if you have one valley seeing that upslope flow with the warm air, and the other side of the mountain also getting that upslope flow of warm air, guess what's going to happen? You've got convergence right over the top of the mountain or the ridge top, and therefore you're going to have a pop-up shower thunderstorm that could just stay there. I've seen this happen along the Tennessee, North Carolina mountains where these storms flare up 1, 2 o'clock and they barely move, and the rest of the area hardly sees anything at all. But we're getting reports of 2 to 3 inches for that person on top of the mountain just because of the air direction and also the wind direction that works out in favor of convection developing in those isolated locations. Once the sun sets, the opposite happens. And we go from a valley breeze, because that's where the wind direction is coming from the valley and up to the mountain, to a mountain breeze. So in this case, we've got the temperature 35 degrees along the side of the mountain, and in the valley, it's 39 degrees. But we have this area cooling down faster because it's higher. It's 3,000, 4,000 feet above the surface. So as that happens, it forms a pocket of cooler air. Notice it's 32 here, and now we drop down to 36. That pocket of cooler air is going to slide its way right down into the valleys. And that's why typically if the winds are calm, you have this classic scenario where the valley, it's 28 degrees or below freezing, and meanwhile on the sides of a mountain, it could be freezing or actually above freezing. And these folks in the wintertime are getting a frost, and they didn't get anything on the side of the mountain. But it has to be calm winds for that to happen. If there's any wind, then the temperature profile will be much different, and this pocket of cooler air won't be able to descend down the mountain and into the valley. Hopefully you learned a lot today, and hopefully I didn't get too much geeking out with the weather, but it's something I always love to explain, just different types of phenomenon of weather. You can always send me questions, nscott@tegna or thv11.com. You can also message me on my professional Facebook page. Make sure it does have, the AMS profile picture and me in a suit. Otherwise, that's my personal page. And I just want everything to be on the professional page when you do message me. Also, if you have any pictures, we always love to get your pictures, 501-376-1111. You can also send those weather pictures to our Facebook pages and the THV11 Weather Reporters. It's a specific site that we are looking for folks like you who are interested in weather, giving us reports, letting us know what you're seeing, what clouds you're seeing, and also, especially with severe weather, we want to know what's going on in your neighborhood. Thanks for watching WeatherWise. I'll see you soon. Have a great day.